Recording in progress.
All right, we're starting 8.1 today. Yeah, we're going back in time. We did chapter 9 first because it feels, I don't know, chapter 8's better. It's not a lot in it, and there's like 3 sections we're doing in chapter 8. And it's more of a this will lead to differential equations class kind of thing. And that's what chapter 8 is on. Modeling. Oh, video. Welcome, everyone. It's been a long time since we got to make a video. This will be on 8.1. Chapter 8 is on mathematical modeling. Thank you. Chapter 8 is on mathematical modeling. So that is code speak for real world applications. And drum roll, please. Word problems. Everybody's favorite fucking topic. We've done several applications throughout this semester, as you've seen, doing certain volumes of revolution, stuff like that. 8.1, we're going to start talking about differential equations. Oh, good. It's so good to be back on Zoom and recording. I like having a database of videos that I can say, hey, if you're not taking my class and take Calc 2 with another teacher, but you still want my shit, and I'm not teaching it, there you go. You can watch a video. So a differential equation involves one or more derivatives. I totally did not know this is what we were talking about today, Michael, because we were going over this shit fucking Wednesday night.
Yep.
Like literally after class on Wednesday night, like I'm really excited about some of the stuff for later on. Differential equations are good. I didn't know it was next. So something like dy dx equals negative 4xy squared. We could have some more shit going on. D squared y dx squared minus 3 dy dx plus 2y equals 0. Sometimes we don't even have like y in it. It could be just like y double prime minus y prime is like 2. These are all examples. We have a derivative might be written as dy dx or d something, or it might just be listed with the prime notation. We will say the order of a differential equation is the highest derivative in the equation. Differential equations come in 2 flavors. A is the ordinary differential equation. Often called ODE. And this is when like the ones we have above, all of these are ordinary differential equations. One variable is a function of the others. I'll put S in parentheses on others. I'm so excited Zoom's working. Before I go on to B, now that I've identified these as ordinary differential equations or ODEs, we can go back up and look at the orders of the ones that are above. This is a first order ODE. And both of these have a second derivative. They are second order ODEs. You will often see differential equations abbreviated diff and then EQ. And it's literally pronounced diff EQ. So if students are talking about diff EQ, they're talking about like a differential equation or the class differential equations. Now the one, and I don't think it even shows up in Math 81 here. The other form of this is the partial differential equation. PDE. I can't remember if this was even available in upper division mathematics. It might be a graduate mathematics topic. It's fucking hard. So this is where like two or more variables are functions of others. You don't even have the integration skills to like contemplate this yet. Someone in here does. She's taking Calc 3, has done integrals of 2 and 3 dimensions, so has an idea of it. But when you've taken Calc 3, you'll have seen where it starts. This is where you might have X is a function of time, and Y is a function of time, and maybe Z is a function of time. And then you've got some equation related to these. But now the derivatives, you have to pay attention to the derivative of each independently. That's the good shit. That's the like, I'm fucking literally unraveling the secrets of the universe astrophysics level shit right there. That's where you can like say, I'm almost a god. Like, if I had the power to create, I would be a god because I know the mathematics that needs to go behind the creation to support the physics of the universe. It's glorious. It's glorious, I tell you. So maybe upper division, definitely grad school. And it's probably not upper division in pure math, but in applied mathematics. Grad school, definitely. And guess what? I had you do one of these or given it to you as an option on one of your tests already. One of your tests, the extra credit problem was this equation. I think it was your guys' class. Fuck, maybe it was Calc 1. Shit, I'm on the top one. This equation meets the, this solution satisfies this equation, show that it does. I don't know if I did that, maybe not, now I gotta go back and look, maybe I'm talking out my ass. Maybe it does math 65. But I'm teaching both of 65 and 66 this semester, and they've got related content. Everyone ready? Everyone looks ready. Okay, so a solution. What is a solution to a differential equation? A solution to a differential equation is a function, not a value or constant, but a function which solves the equation. I.e., plug it in and it makes a true statement. And we'll look at an example. The first one I wrote down was dy dx equals negative 4xy squared. Verify that y equals 1/2 x to the negative 2 is a solution to this equation. I know the Calc 3 classes are filling up. At break time, I'll talk to you about a strategy you can do to, if you haven't gotten in yet and plan on taking it, what you can do to try to get it. All right, so I've got y equals 1/2 x to the negative 2. If I hit this bad boy with a d dx, I get dy dx equals 1/2 times negative 2 times x to the negative 3, which is negative 1 over 2x cubed. And this one rewritten is 1 over 2x squared.
Wouldn't that cancel out the 2 on top, 2 on bottom?
Yes, it would. So what we're trying to show, thank you, we want to show that negative 1 over x cubed equals, I'll put a question mark over it because we're verifying it, negative 4x times 1 over 2x squared. That's what we want to check. Go ahead and run through that algebra for a quick second. Shouldn't take you long. Dalton emailed me, asking if I was extending the homework due date since our test isn't until next Wednesday. I had forgotten to do that. It has been updated to be next Wednesday. So if you haven't submitted yet, you still have plenty of time. Thank Dalton for that reminder. And a lot of times students won't email and ask. All you gotta do is ask. All right, so if we went through this and did it, what do you get? And if I put that over that, looks like the fours will cancel. And this X will cancel out one of those X's there. And I am indeed left with -1 over X cubed. So note that this was a function. Not a constant. All right, so a general solution or the general solution for an ODE. Well, PDE also, but PDEs are more complicated. Let's just say ODE for now. Is a solution containing arbitrary values. Or constants from which all solutions can be obtained. Oftentimes, this is called a family of solutions. Usually, the number of arbitrary constants I fucking spelled that wrong. Arbitrary constants is equal to the order of the ODE. Couple people are still writing, so hang in there if you're done. Dalton really likes me. He keeps coming back. I saw you're enrolled in Calc 3. I approve. What? Thank you. I probably do less than half the work of learning here. I only lead you to the river. Whether you learn well is whether or not you're motivated to learn one and to put in the effort to learn. But if you're doing well in here, it's more on you than anything else. As long as like the tests are challenging enough that indicates you're learning something. I could give you an easy, like everyone in here can get A's, but that doesn't mean you learn Calc 2. You know what I mean? I could make tests super fucking easy. All right. People look like they're done writing. So we will talk about in 8.2 and 8.4 processes to find these general solutions. For now, we're just going to verify. And if I have time before the class ends today, we'll start 8.2. 8.2 is probably my favorite topic in all of Calc 2. It's even better than fucking the Taylor and Maclaurin series. And that shit makes waves into fucking polynomial equations. That's good shit. I like 8.2 even better. Okay, so we had dy dx. We're going to go back to that bad boy being negative 4x y squared. Show that y equals negative 1 over 2x squared plus c is a general solution. Now, I think this is going to be a little bit easier because I don't want to do the fucking quotient rule. I don't know about you. But I'm going to rewrite this as negative 1 times 2x squared plus c to the negative. This allows me to do product rule and chain rule and avoid the quotient rule, the godforsaken quotient rule. When I do ddx or find the derivative, y prime is going to be negative 1. That's the negative 1 we had out front. Then that's the negative 1 we bring down. We lower the power by 1, so it goes down to negative 2. And then we do ddx of this bad boy, and we get 4x. So this is, when we wrap this all together, dy dx is, looks like the negatives cancel out, and I have 4x over 2x squared plus c squared. Wait a second. That was not supposed to be negative. That was supposed to be positive. My bad. That just changes that positive makes this negative. I'm like, this isn't going to happen. This is going to have a negative. Where is this fucking negative coming from? We were going to show that that wasn't a solution. That's what we were going to show. So we're going to make that y positive. So this should equal negative 4x times y squared is 1 over 2x squared plus c squared. That's my y squared. So we're doing that part right here. And that's the condition we're trying to check. I'll put a question mark over it, and there's not a lot of work here to do, is there? I can break this up to do the square on top over the square on bottom. But the top is just 1. And we get negative 4x over 2x squared plus c squared does in fact equal negative 4x over 2x squared plus c squared. C can be any value. Just a second ago, we used y equaled 1 over 2x squared, or 1/2 x to the negative 2 is what we had called it. In that equation, c equals 0. But it could be anything, as long as it's a constant. It could be 1, it could be negative 1,000,000,000, it could be e, it could be pi. Fuck, it could be e to the pi. There's some mind fuck for you. Any questions about the general solution? Is this, it's not that bad right now, is it? This is pretty easy. I think today's lesson is really fucking easy. So that's the general solution. A particular solution is where the arbitrary constants are given values. Based on something called initial conditions. So back to our example. dy dx equals negative 4x squared, 4xy squared. We saw that y equals 1 over 2x squared plus c is the general solution. I'm going to give it the initial condition. Y of 0, often called y0. Oh, I don't know. What do you guys want to call it? Equals 2. Fuck it. Let's do 2. So when you have the general solution, you basically just plug this shit in there and it pops out like this. Y of 0, which is 2, equals, this is saying x equals 0 there. 1 over 2 times 0 squared plus c. So I have 2 equals 2 times 0 squared is just 0. I have 1 over c. And this is gonna lead us to c equals 1/2. Which you can see if you just multiply both sides by c over 2. So the particular solution here is y equals 1 over 2x squared plus 1/2. Or if you don't like complex fractions, multiply it by 2 over 2. 2 over 4x squared plus 1. You guys ready for more? Okay. Anyone need it longer? Okay. So in general, when given a differential equation, with initial value conditions, for some problems at some point, you will also see the term boundary conditions for some problems. Because initial conditions is like saying something is changing with time, and we want to know what it was like when at a particular time. But it might not be a time, it might be a region, and we're looking at what happens at the inputs. You all right, Dad? You got a headache? Look like you're in pain. I know my voice is obnoxious. My wife tunes me out, but hopefully it's not hurting anyone. So when given a differential equation with the initial boundary conditions, A, find the general solution. Should be found first. And then B, apply initial conditions to identify the constant. So in our next example, our ODE will be x dy dx minus 2y equals 2. And the general solution, since we haven't covered how to get them yet, is y equals cx squared minus 1. And we will have an initial condition or initial value. Let's go with what I have here. Let's use y of 3 equals 4. So first off, let's verify this is a solution. Let's verify that's the solution. If I do dy dx, I get 2cx. All right, straightforward so far. And then we're going to plug that into our ODE. I have x times 2cx minus 2y, but y is that cx squared minus 1 equals 2. All right, multiply. We've got 2cx squared. When you distribute here, make sure you distribute the -2 to both. I get minus 2cx squared plus 2. Does that equal 2? And we will see that 2 does equal 2 when we're done. Now, before I use the initial value here, I want to kind of like illustrate, because this one's easier to draw. I know what this shit looks like. Let's draw this. It's a parabola opening upward. If C is positive. If C is 1, two, 4. Bless you. That's the C equals 1 curve. Let's see, if I do C equals 1/2, what happens? If I go out 2 like this, and then 4, this is like C equals 1/2. And if I just tighten it up just a little bit, that's kind of like C equals 2. So that's why we call this, and that's just a few of the C's. This is why we call this a family of curves. All of these satisfy that equation. So out of all those, since there's like basically an infinite number of these solutions, an infinite number of options, if we're applying it to a real life problem, we need some condition that we apply to it so we know which curve we're picking out of these. Does that make sense? That's kind of the point of the initial value. The initial value picks out one of these. So we're going to plug in when x is 3, y equals 4. I have 4 equals c times 3 squared minus 1. God, that looks like shit. It's fucking bothering me. That's at least a little better. All right, we keep going with this. I've got 4 equals 9c minus 1. I'll add 1 to both sides. 5 equals 9c. Divide by 9, and I get c equals 5/9. So the actual equation we want to pick out will be y equals 5/9 x squared minus 1. Five ninths is close to 1/2. So it's closest to this green line. Gonna be something like that. A little bit off. And it's 5 o'clock. Let me give you a 10-minute break. All right, let's continue talking. Let's do another one where we do a full verification on some stuff. Kick it up a notch. Let's verify that y equals c1 e to the negative 2x plus c2 e to the 3x is a solution to y double prime minus y prime minus 6y equals 0. We commonly use C1, C2, C3. But you could use different letters. You could go with like A, B, C if you wanted. And then we will apply using y0 equals 1 and y prime of 0 equals 8. Find the IVP solution, which is initial value problem. That's what IVP is. Show you some other terminology you might see along the way. We're just taking derivatives, right? Enrique, help me. What's the derivative of y there? I'm gonna throw you under the bus right now, because you're looking at me. You made eye contact.
I always look at you though. Did you actually want me?
Yeah. This is an easy derivative.
I hate being thrown on the spot.
Easy derivative, you can do this.
I hope so.
What's the derivative of the first one?
So we're gonna use the product rule, right? Or is C?
C1's a constant, you don't need to do a product rule.
Oh, okay.
Just take the derivative of E.
Oh, okay, -2, is it X or no?
No,
Okay, C1, E to, -3X? Or is it -2X?
It's- it still stays as that. The 3x is on the other one, we gotta do that one separately.
Oh,
If I do that second one separately, you're taking the derivative exponent. Right?
really cool, that's fine.
Look at this MFer. You think you fucking know what you're talking about, Mr. Jones? You don't know shit. That's not why, that wasn't why at all. Said why up here, it didn't have a fucking -2 or 3 anywhere. You're right, it was by parent. So. We do it again, take the derivative again. We bring down another -2. I'll write it like this for now. To show where it's coming from. This is 4C1 e to the -2x plus 9C2 e to the 3x. So we want to plug in y prime. I'm going to put some space here and I'm going to write underneath it. This is what we're plugging in.
Why do you square the 3? It will be 2?
Because I'm bringing it down again.
Yeah, it's a 3.
Yeah, but it's 3 times 3.
Oh. See, I'm a little slow.
I get that. I mean, I get the 3 cubed. Not that you're a little slow. That's he's looks back there like, God damn, he's fucking him up there. Just fucking just slay. I'm gonna fucking report Mr. Jones. He's abusing fucking Enrique. That is not what I meant. You're like, it's on video. I can send this video in.
It's gonna be the uniform version.
Right? All right, so plug in what we got in. This was my y double prime. So this is 4C1 e to the -2x plus 9C2 e to the 3x. And then I'm doing minus, and I'm going to use parentheses so that I can just plug it in and distribute afterwards. -2C1 e to the -2x plus 3C2 e to the 3x. And then I've got minus 6 times what we started with, C1 e to the -2x plus C2 e to the 3x. All that has to equal 0. As long as you go slowly and you remember your derivatives, this is a relatively easy task. If you don't go slowly and try to rush it and like not pause to write everything out, you will fuck a sign up somewhere. Like if I didn't put this in parentheses and just start doing negative this, it only takes your fucking phone, that text message vibration to go off. You get distracted. You've applied the negative to this one, but not to this one. Your shit doesn't work. You're like, I don't know what, more often than not, the first thought is, I don't know what the fuck I'm doing, not, I made a mistake. So like, always go back and check your stuff like that. But if you've taken the time to actually write it out, which does take longer, you can verify what you did each step of the way. All right, so this is 4C1 e to the negative 2x. I'm just gonna do the distribution for now. Distributing the minus makes this plus 2C1 e to the negative 2x, and then minus 3C2 e to the 3x. And if I do the negative 6, I've got negative 6C1 e to the negative 2x minus, I almost said plus, minus 6C2 e to the 3x equals 0. Now, a lot of these have e to the negative 2x with a C1 in it. That has C1 e to the negative 2x. That has C1 e to the negative 2x. That has C1 e to the negative 2x. I can factor out all their coefficients out front and put C1 e to the negative 2x like that. Just factoring out the coefficients. Then I'll go to my C2s and do the same thing. I've got 9 and a minus 3 and a minus 6 times C2 e to the 3x equals 0. And that's 0 and that's 0, so 0 equals 0. Ta-da! Ready for another? I got more. Don't you worry. You're right. I was about to turn the page. I haven't done the IVP part yet. Thank you. All right, IVP part. So we had two conditions. We had y of 0 equals 1, and we had y prime of 0 equals 8. If I apply these, I've got y of 0. This is when x equals 0, y equals 1. This generates 1 equals C1 e to the 0 plus C2 e to the 0. Which gives me 1 equals C1 plus C2. Or 1 minus C1 equals C2. I imagine we're going to have the same problem. The other one we're going to have to do, we're going to have two equations with two unknowns and have to solve. It is convenient on a lot of them, especially when you have exponentials and like trig functions. They will usually use something that makes the hard part go away or the shitty part go away. Like notice the e's are gone. When I do y prime, I'm going to this one. I'm saying that y prime equals 0 is 8, negative 2c1 e to the 0 plus 3c2 e to the 0. or 8 equals negative 2c1 plus 3c2. So as an option, you can do substitution. I actually like substitution the least. I think with this having a -2, we can also use the addition or elimination method. If I multiply this by 2, I get 2 equals 2c1 plus 2c2. And I just add vertically. 10 equals 0c1 plus 5c2. And this is going to show us c2 equals 2. If you had done substitution, you would have 8 equals negative 2c1 plus 3 times 1 minus c1. And you would have found c1 first, but we're going to find c1 real quick. Take c2 equals 2, plug it in. 1 equals c1 plus 2. So c1 equals -1. And that means my equation, particular solution, is negative e to the negative 2x plus 2e to the 3x. Ready for another? Okay. Easier to read if I put it where it's lined up a little bit better. Yeah, I love this. Verify that y equals e to the negative 2x times c1 sine 3x plus c2 cosine 3x is a solution to y double prime plus 4y prime plus 13y equals 0. Yeah, boom. Let's just go straight challenging right away. Like third example. And then our IVP stuff will be y of 0 equals -1, and y prime of 0 equals -1. Now you can either distribute the e to the negative 2x now or go with the product rule as is. There's going to be some product rule going on. I'm just going to take the derivative as is. So if F is the e to the negative 2x part and G is the rest, I've got F prime G plus FG prime I need to fill in. So F prime just brings the derivative of negative 2x is negative 2 e to the negative 2x. And then I've got C1 sine 3x plus C2 cosine 3x. That's my F prime G. And then my FG prime is, oh, got to put it in, e to the negative 2x for F. Sine goes to cosine, stays positive. We bring out the 3. And I need a C1 in there. And cosine goes negative, minus 3C2 sine of 3x. This is ugly already, isn't it? Now, I can make it a little bit better. I don't know if distributing or anything like that's going to help, but factoring out the 3 might make this part a little bit easier. And then I pull out the 3 here and have C1 cosine 3x minus C2 sine 3x. Oh, Nelly. You definitely want to do the general solution first before you do the initial value problem. We could do the initial value problem and find out what one of these letters is right away using this, but you don't want to. In general, you want to have the general solution available so that you can use it for other initial values. Like if you're doing a project when you're actually using this in real life. All right, so now we go on to the shitty one, because that was the easy one. So this is like A times B plus C times D. And if we do the derivative, we need A prime B plus AB prime. And then plus C prime D plus CD prime D. There's a lot of shit going on here. So we might have to do this over 2 lines. Let's focus on the AB portion first. Just focusing on this one. That's my AB. So if I do the derivative here, again, I'm doing the derivative of the exponential first. I have 4e to the negative 2x times C1 sine 3x plus C2 cosine 3x. And then I got to do the derivative of the inside. And we actually did the derivative of the inside over here. I can just copy that shit down. 3C1 cosine 3x minus 3C2 sine 3x. And then we'll do our CD portion, the second part. If I take the derivative of the e to the negative 2x, this is negative 6 e to the negative 2x. C1 cosine 3x minus C2 sine 3x. Gotta go slow on this shit, right? There's a lot of room for fucking making mistakes. Making mistakes sucks. Then we gotta take the derivative of what's on the inside here. This is gonna be negative 3C1 sine 3x minus 3C2 cosine 3x. All right, so putting this all together. It looks like I have some C1s with e to the negative 2x. And then sine 3x and cosine 3x. I'm gonna like this is a C1 sine 3x. And this is a C1 sine 3x. So I'm gonna like underline them as I do them. I've got C1 sine of 3x times, there's an e to the negative 2x, and I'm writing this in a funky order. Then we've got a 4 plus a 3. If we distribute. No, this is minus 9. Learn to distribute, David. So this times that, and this times that. I got the C1, I got the sine, I got the e to the negative 2x. I've also got C1s with cosine. So I'll do those. Maybe I'll leave some room in the front for the coefficients so I don't look like a total moron. And my coefficients on that is negative 6. And then it looks like minus 6, another minus 6. Negative 6C1 and negative 6C1, okay, and then 4C1 and negative 9C1. Okay, those are good so far. And then C2, I'll do double underlines. We'll start with the cosine x's right there. So then I've got plus, I'll do a parentheses. We're going to do the C2 cosine 3x's now. And we still got e to the negative 2x and all this shit. And if I do the cosine 1, this is 4 times that, which is 4. And I have 3 times negative 3 is minus 9. Interesting, this is following the pattern here. Yeah. Yes. So I should have had, yeah, that's a 4 minus 9 right here. And I wish I had put it in front. And then we've only got a couple things left. C2 sines. So my C2 sine 3x, e to the negative 2x, has a negative 6 times a negative 1 is positive 6. And then I've got a -2 times a -3 is another +6. So if I were to clean this up, well, first off, I'm gonna pull the e to the -2x out of all of them because it can go fuck itself. Then I can focus on the sine 3x's. Sine of 3x has 4 minus 9 is -5. -5c1 plus 12c2. And then I'll have a parentheses for the cosine 3x. And let's see, what I did there was this one. And that one. So now I want to do this one and this one. I've got -12c1 and -5c2. That's about as clean as y double prime gets. We could probably make y prime a little cleaner if we did something similar. Let's put the e to the -2x there for y prime. Let's make a nice clean form for this. And let's see, on this sine 3x, that's what we did first here. I have -2c1 and -3c2. And now we're looking at the cosine 3x here. Cosine had -2c2 and 3c1. I sure hope I didn't make any mistakes because we're gonna find out when we plug them into the initial problem here real quick. I don't know if you like the process of underlining shit in different ways, like one underline, two underlines, a wavy underline, and then a double wavy underline. And kind of like if you got to look back and see what you did, like if I have like a mistake, it allows me to look back and like see what I did, maybe find a mistake rather than starting over from scratch, which is a bitch. All right, we're trying to do y double prime plus 4y prime plus 13y. Let's see how this stacks up if I put them in the same order here. I've got the e to the -2x, -5c1 plus 12c2 sine of 3x plus -12c1 minus 5c2 cosine 3x. And then I need to do 4 times my y prime. I'm not gonna put it out front. I'm gonna put it on the inside. I'm gonna multiply each of these by 4. So I would have -8c1 minus 12C2 sine of 3x plus, and I'm doing 4 here, 12C1 minus 8C2 cosine 3x. And finally, I need 13 times the original one. Gives us a 13C1. And I put a positive there to show it's positive. I don't know why. I'm not gonna do that. That looks stupid. 13C1 sine 3x. And then I've got a 13C2 cosine 3x. And now the way I did it, I can add these vertically. So I've got negative 5C1 minus 8C1 plus 13C1. And then plus 12C2 minus 12C2 sine of 3x. Plus negative 12C1 plus 12C1. I should say C2 right there. Minus 5C2 minus 8C2 plus 13C2 cosine of 3x. And the only reason I did it like this is so I can go back and verify my work later on if there's a mistake. You could have probably done this a little faster and seen that the C1s cancel out and the C2s cancel out for both of them. Those cancel and these cancel. So I'll have a 0 for those. And those cancel with those. So I'll have a 0 for those. So this is e to the negative 2x times 0, which is 0. It does equal it. It worked. Which is really good. There was a lot of shit there and I didn't want to fuck it up. It smells like a test problem. Maybe an extra credit problem. That's a little complicated for a test problem. I don't know. This is a lot of work, but was it all that hard? It's tedious. Tedious more than anything, right? Trying to keep track of everything. In grad school and applied mathematics, here I had this shit on 2 lines. In grad school, I would have something that had fucking 5 lines, smaller font because I'm writing for myself rather than trying to write where I'm big on the screen, still taking up 5 lines of shit and trying to keep track. That's where I developed this whole underline thing to help me follow what the fuck I've been doing. That's madness. Madness, I tell you.
The hardest person's taking to follow your own.
Right? All right, we have not finished that though. We need to do the IVP. So y0 equals -1 and so did y prime is 0. If I stick in -1 for y, I've got -1 equals e to the -2 times 0 times c1 sine of 3 times 0 plus c2 cosine of 3 times 0. So -1 equals 1 times C1 times 0 plus C2 times 1. Looks like C2 equals -1. I do Y double prime, not double prime, single prime. That also equals -1. I'm gonna plug it into this one right here. Let's do IVP on this one because that's the cleanest form we had for the Y prime. I've got e to the -2 times 0, -2C1 minus 3C2, but C2 is -1. That's my C2. And then I've got sine of 0. Ah, that's candy. That all's going away. No one cares about it anymore. And then I've got, plus 3C1 minus 2 times -1. That was my C2 times cosine of 0. This is 1 times 0 plus 3C1 plus 2 times cosine of 0, which is 1. So what do I have here? I've got -1 equals 3C1 plus 2. I'll subtract 2 from both sides. And look at this MFer. C1 is -1 also. So the particular solution or IVP solution, they're both -1. I'm coming up to here, they're both -1. I'm just going to factor out the -1. Y equals -e to the -2x sine of 3x plus cosine 3x. My next example, before I start spitting off a list of relevant applications. Y double prime plus 4x equals 0. Y0 equals 1. Y prime is 0 equals 2. And we're going to solve by integrating. I'm not giving you the solution. We're just going to generate it as we go. So to start off, I will subtract the 4x over to the other side. And then we're going to integrate with respect to dx on both. This is going to go up to y prime. The integral of this is up a power divided by a power, -2x squared plus a constant. I'm gonna call that C1. And if I integrate this with respect to dx now, I get y equals up a power divide by the power negative 2/3 x cubed plus c1x plus a second constant. We start applying conditions. Y is 0 equals 1 equals everything here at x equals 0. 0 cubed plus c1 times 0 plus c2. So c2 equals 1. And then bringing this one down, that was our y prime was negative 2x squared plus c1. We're going to do y prime is 0 here equals 2. That's negative 2 times 0 squared plus c1. So c1 equals 2. And our particular solution is negative 2/3 x cubed plus 2x plus 1. All right, some areas that we're going to apply this to that we'll see. So like population growth. This is an unlimited one. dy dt equals ky with initial conditions of y0 equals y0. K is called the growth factor. And this has an exponential solution, as we'll see tomorrow. Exponential solutions, if we had unlimited growth, you're going to have an infinite amount, an astronomically high amount after a short period of time. So unlimited population growth is very unrealistic. This is unrealistic. But it does give us an idea of how things are modeled. A better one is the logistic growth model. And it comes in two flavors. They both have dy dt equals ky, and then times 1 minus y over L, where L is an upper bound or population cap. This one will tend to, if this is L, it'll grow exponentially until it gets close, and then L acts like a horizontal asymptote and caps out. If it goes above it, it swings back down to go underneath it and fucking rise over asymptote. Usually if it hits L exactly, this becomes 0, so dy dt is 0, and there's no growth. So it'll stagnate there. That's not entirely the way. There's also the minimal one, which has the same elements as the logistic one. But then it's got, I'm going to use M here. No, we use M for slope. Let's go L2 over Y. L2 here is a lower bound or minimum population. And you do enough of this, you'll see these all have exponential solutions. Another one related to this one is the annuity growth. Dy dt equals ky plus p. K is still growth. P is money entering or leaving the system. This is when you're making your retirement. If you're making like monthly contributions to it, it's following a upwards growth, but it's also adding P, whatever you put in each month. Like, let's say you make a lot of money, you're able to fucking throw in $500 to your retirement each month, which is a good chunk of money to throw into retirement each month. That's the P. When you retire, P goes negative, you start pulling money out, but it's still earning it. This models the interest. This is the interest. But when you're pulling out, P is the negative, and so it's how much you're withdrawing each month. And one last one. Newton's law of cooling. You will see this in physics, guaranteed. dt, big T is temp, little t is time. dt equals k times t minus ta, where ta is the ambient temperature. In modern life, we call that the room temperature. But if it's in like a fucking freezer, it's not room temperature. And this one has like an initial condition of T0, they tend to call it. All right, there's a couple minutes over, sorry, but those are like the different, wanted to like introduce you to them. We walked through a bunch of hard examples, well, extremely hard example. Well, tedious. I don't know if it's hard, but tedious, long. And on Wednesday, we'll start talking about, it's called separation of variables, my favorite fucking topic.
It got me 15 lines basically completely filled in left to right.
Right. It's about a lot of work, isn't it? All right, I will see you guys on Wednesday. Don't forget, we have a test the following Wednesday. Godspeed, GTFO.